Okay, so we're very happy to have Aron give us our next edition of the Quantum Spacetime Seminar. Aron, over to you.
Okay, so let's try to share the screen again. Let's see if these operations don't quite commute. So I'll do that. And then I'll do that. All right, can everybody see the slides? Great. Okay.
Yeah, we can see this.
All right. So I'm going to talk about Cauchy slice holography and the information paradox. Now, I gave an earlier version of this talk online and from Qubit meeting at the IS, but I was staying home at the time because I had a very high fever. So hopefully this version of the talk will be more coherent than the last version. So this talk is primarily based on three papers. So there's the original Cauchy slice holography paper that I wrote with my then PhD students, Gonzalo and Rifat. There's a paper on the covariant edge rebound from Cauchy slice holography that I wrote with Ronak Soni, and there'll be a sequel coming out soon where we add matter and discuss the information paradox along lines somewhat similar to how I'm going to be discussing the information paradox in this talk. And perhaps I should also mention that Gonzalo is working with my current PhD student, Aron on the DS version of this story, but I'm not going to be talking about that in this particular talk. So one research goal that I'm interested in pursuing might be expressed by a sort of oxymoron, which is what is local holography? So on the one hand, we know from ADS-CFT that the information in the quantum gravity state must somehow be encoded on the boundary. On the other hand, to make contact with semi-classical bulk physics, we want some sort of local description of the theory, and that local description should be somehow telling us how information flows out to the boundary according to local rules. So the reason this is an oxymoron is holography says the information isn't localized, but we still need some sort of locality in the rules for how it isn't localized. So this was basically the goal of the tensor network program that there was a lot of work on with it from Qubit, but that has difficulties accounting for the sub-ADS scales and for dynamics. So the approach I'm going to be telling you about that is based on TT bar stuff can handle these things. So the idea of Cauchy slice holography is that there exists a field theory whose partition function is equivalent to the wave function of a quantum gravity state with an emergent time dimension. So usually in ADS-CFT, we have one, well, there's also the compact dimensions, but if we ignore that, we have an emergent space direction. And in the case of this model, we want to instead think of it as an emergent time dimension. So the way that dictionary would work is I have, can you guys see this cursor? There's an arrow
Yeah,
hovering around. Yeah, okay, good. So the you have a partition function of this TT bar theory, and it depends on some fixed QFT background sources in little d dimensions. And so that includes a metric, just in the way QFT normally depends on a metric. It could involve some scalar sources, some list of sources. And this we want to think of as functionally depending on these sources in the same way as a Wheeler-DeWitt wave function, except now we interpret the things it depends on as the configuration space variables of a theory that is in d plus 1 dimensions. So there's a very natural dictionary relating both of these sides because in both cases, what we're interested in doing is differentiating with respect to fields. When you have a partition function and you differentiate with respect to the metric, you call that the stress energy tensor. On the other hand, when you have a Wheeler-DeWitt state and you differentiate with respect to the metric, you call that the ADM momentum operator. Now, there's some unimportant convention differences here involving whether you densitize in factors of two and that sort of thing. That's not very important. But there is a very important difference in this thing, which is this I sign. So that's the thing that should be bothering you most about this statement. And it's actually going to end up implying that this the theory we're taking the partition function of can't actually be a unitary theory because its stress tensor ends up being imaginary when the ADM momentum is real. Nevertheless, we can still study this theory. There's the same relation for other operators. For example, if you take a scalar source, you get an operator in this field theory or its corresponding momentum. Now, the particular theory that I'm going to, this TT
Sorry.
bar, yeah.
We can't see the last lines of your equations. We
Oh
see
dear. Where does it, what's the last thing you see?
we see the equation which is O which is equal to del by del phi is equal to I pi, and then we see by construction the theory satisfies the Wheeler-DeWitt constraint equations, but we don't see what's below that.
Okay, so you're missing one line and it's text actually.
Okay.
It says, so gravitational dynamics is included automatically, unlike tensor network models. Okay, so yeah, I'll,
One question about physics, not about yeah.
yeah.
So your left hand side is firstly it's a partition function of a Euclidean field theory, right? Because it's like a space-like slice.
That's right.
Okay, and this Euclidean field theory is on a non-compact space because it extends all the way to the boundary of ADS.
Yes, in this case.
And you apply some, in order to make this thing well-defined, you need to give your field some boundary conditions on this slice.
That's correct. I'll answer this question later, but the answer is that the boundary conditions are a normal CFT state in the NES CFT that this theory is defined from.
So that the field dies off like it should, given its expectation values in.
That's right. So to anticipate, yeah. So this theory is going to be defined as an irrelevant deformation of a standard ADS CFT, and so in the limit that you approach the boundary, the vowel factor goes to infinity, and you recover the original CFT. And that in particular implies that you can junction it at the boundary with a normal CFT state. And that is actually allows you to get the dictionary between Wheeler-DeWitt states and normal ADS-CFT states. You just plug in as your boundary whatever CFT state you're interested in studying the bulk geometry of, and then you evaluate this partition function.
Just
Yeah, there's another question.
yes. So usually in ADS-CFT, I mean the boundary also has time, which is same as the bulk time. So in this case, I mean this looks more like the what one would say for de Sitter or something, where you have, I mean, apart from the TT bar part of it, where you have a field theory, its partition function would be a Wheeler-DeWitt wave function.
That's right. But because it has a boundary, you can study multiple states of this theory. And so the spectrum is the same as the ADS CFT. And here, let's go to this slide, since this is what we're discussing. So I guess I already answered this, the first thing. So if you have your boundary state here and you want to evolve in time, you could do so, for example, by gluing some amount of cylinder evolution of the usual CFT field theory to that. So if you wanted to calculate a transition amplitude between two Wheeler-DeWitt states with some gravitational path integral between them, you could do so on the boundary side by taking two such slices and gluing them together using well, it could be you could just does that answer the question?
Sorry, we couldn't hear the last half a minute.
Oh, yeah. Yeah, sorry about that. So the you can what I'm saying is that you can glue you could do path integral constructions that glue two Cauchy slices together, and that corresponds to calculate the gravitational path integral between these two slices with zero time difference on the boundary. And then you can also glue them together with some delta t time difference on the boundary, just by gluing in a segment of normal CFT evolution. Does that make sense? Did you get that?
On the blue shaded area or just on the boundary of it? You say codimension.
Let's see if I have a picture of this. No, I don't. I could find it somewhere else. Okay, so here, let me show you in the paper. Uh, so let's see. Just share my overall screen. Can you see my screen now? No, wait, this is the wrong paper. I want this one. Let's see. So you can glue two Cauchy slices together in a way that shares a boundary. And then you have a sigma 1 slice and a sigma 2 slice. And from the boundary perspective, this is like a closed partition function, so you get some number. But the holographic dual description is that there's a gravitational path integral with these boundary conditions, and you're calculating the path integral over this G, which is might be dominated by some classical saddle. And then if you want to get time evolution, you would do something similar, but with some amount of boundary CFT time, which is the sides of the cylinder. So the caps at the tops and bottom would be this deformed theory, and the side of the cylinder would be the uh, the Cauchy slice holography theory.
Okay, thank you.
All right. So let's see. Uh, if I return, so now I'm going to be, can you see this whole slide now? So I'm doing it differently. Can you see the bottom of the slide now that says unlike tensor network models?
Yes.
Yes, good. Okay, great. So, all right. So I've discussed what happens when the Cauchy slice is open so that you have the state on the boundary. It's more confusing what to do if you're doing a closed universe. as you might want to do in the cosmological case. In that case, the partition function of the theory gives us just a single Wheeler-DeWitt state, and that's more puzzling from a philosophical point of view, although it's compatible with what people say when they're doing DSCFT, where they think of the dictionary as being to a specific preferred state, like Hartle-Hawking. So it could be that in the cosmological context, holography picks out a particular state for you.
Aron, if you take a field theory and deform it by a source in some nonlinear way, typically you need UV data. I mean, typically that's not well defined.
That's right. So the you're talking about the usual Wilsonian issue of irrelevant terms.
You would
Yeah,
have irrelevant operators.
irrelevant operators. That's correct. This is an irrelevant deformation. So I guilty as charged. In my view, the biggest open problem here is to find a way to UV complete this theory. And I believe if it were UV completed, it would be a definition of manifestly holographic non-perturbative bulk quantum gravity. So if it's sort of important that that's an unsolved problem, because if it wasn't an unsolved problem, I'd be making far more grandiose claims right now.
Some limit in which this is unambiguous.
Yeah, so in large N, the flow equations map onto classical GR, and in that limit we can understand it pretty well, as long as you stay away from the Planck scale. So so let me move on to let me show you this deformation. So the way you get it is if you start with a case of ADS-CFT. So you have a negative cosmological constant. You could do similar things starting with DSCFT, except there's less examples of that. So if you start with ADS-CFT, you can obtain it by deforming it by this irrelevant deformation known as T squared. And the reason it's called that is that the deformation is quadratic in the stress energy tensor. So it involves this particular combination of, stress tensor terms that has to be in this proportion. And then there's some terms that depend on the matter and the curvature that depend on the details of what dimension you're in and what your bulk matter sector is. So, but the point is the entire deformation is chosen so that when you deform your theory, the trace equation for the stress tensor deforms into the Hamiltonian constraint equation. And you automatically satisfy the spatial diff constraint equation just because this deformation is covariant. So uh, the these terms can have various dimensions from the perspective of the CFT, but the stress tensor squared one always has dimension 2D in operator terms, or minus D as a source, which means that it is an irrelevant operator. So for the usual reasons, you should worry about it in a Wilsonian sense. Now, in the original Zemeljakov version of this for two-dimensional CFTs, there was a special factorization property that ensured that the spectrum continued to be well defined for arbitrary sizes of this deformation. This does not apply. This has to do with the fact that holographically it matches onto pure gravity in D equals 3, which has no local degrees of freedom. In the case where the bulk has local degrees of freedom, you don't have this Zemeljakov factorization property, but at large N, you have a different factorization property that is due to uh, to the holographic nature of the theory. And that just tells you that if you take the expectation value of this quadratic type term, you could just break it up into the product of two expectation values at large N. And that makes it so that the deformation is better defined than you would think it would be. In particular, it means that when the deformation gets strong in the usual Wilsonian sense of strong, you are just probing some ADS scales, and the theory is still consistent, or appears to be consistent. Where you get into trouble is where you actually try to evaluate this theory at the Planck scale, which at the holographic limit can be a much smaller scale. To define the theory at the Planck scale, it's important to think about UV completions. I have quite a lot to say about that, which uh, if those of you interested in this topic, I would suggest you view my recorded talk at the IS when I was on sabbatical there about discrete symmetries in TT bar. Okay, so the the deformation is defined with a coupling constant. That's this mu here. And it's important that this is actually a viewed as a flow equation. So as soon as you change your Lagrangian of your theory, your definition of your stress tensor changes. So you have the question, do I use the stress tensor as it's defined at the beginning of the flow, or my stress tensor as it's defined at the end of the flow, or what? And the answer is you're always supposed to use the stress tensor at whatever is the current moment of the flow that you're at. So if I integrate mu from 0 to 1, then I have to think of the Lagrangian as changing by this differential equation where I didn't write it, but these stress tensors are implicitly a function of mu. It's the stress tensor at whatever value of mu you have. Now, it's convenient, and by convenient, I mean changes the story so you only have a finite number of terms to worry about instead of an infinite number of terms. So I mean very convenient here. It's very convenient to arrange things so that mu is the only dimensionful coupling constant in this deformation, so that all other coupling constants scale in the appropriate way with mu. And if you do that, the exact value of mu doesn't matter. You need to make sure mu has the right sign to do holography, which is the opposite of the sign that gives you a unitary theory. But after that, you could, if you like, just set mu equals 1 and think of the different questions that you could have asked by varying mu as just changing the metric in various ways, so that you just evaluate this theory at different scales. So because the deformation is irrelevant, for the usual reasons, you could worry that theory's ill-defined. Okay, this is stuff I said. But the holographic regime, uh, so at least at leading order and n, and I believe you can probably do it in every order in 1 over n, the spectrum of the theory on a cylinder is solvable. So in this regime, the theory seems to be well defined. However, something quite strange happens, and it happens in the regime that is far from the Planck scale. So this is not a Planck scale effect. At a certain point, there's a branch cut, and the energy eigenvalues become imaginary rather than real. And as a result, this theory is not unitary. So you could say there isn't a norm, but it's probably better to say there's some indefinite norm of this theory that is, but there's no positive norm that's preserved by real-time dynamics. When I say this theory is not unitary, since we're going to discuss the black hole information puzzle here, it's important to clarify that non-unitary has multiple meanings. I do not mean non-unitary in the sense that people discuss with the black hole information of pure states evolving to mixed states. That is not what is happening here. This theory has pure states evolving to pure states. It's just doing so according to a Hamiltonian that allows for some eigenvalues of the Hamiltonian to be imaginary rather than real. Now, this was actually inevitable, as if you go back to this dictionary here, if I just interpret a Wheeler-DeWitt state as a partition function, I quickly discover that it does not have the reflection positivity property that encodes unitarity in a Wick-rotated normal Euclidean field theory. So it's inevitable that if we're going to study this thing, we have to start thinking about non-unitary theories. But I was somewhat emboldened to do so by the fact that people already knew they had to give up unitarity when they were doing things like DOCFT. And so it seems clear that the bulk being unitary doesn't always map onto the boundary being unitary in every form of holography. Now, there's also a difference between TT bar as studied at, say, Stanford and as it's studied at Cambridge. So a lot of the people who are working at this in other groups have argued that you should view TT bar as like a UV regulator and throw out these imaginary energy eigenvalues so that you get some sort of non-local theory with a finite number of states. But if you want to do this Cauchy slice holography, it's actually crucial that you do not throw out the imaginary energy eigenvalues. They're actually the interesting part of the physics because they are the states that map on to a Lorentzian signature dual bulk. If you look at the real ones, then you can't do that. So here's a picture of the spectrum. So if you have a holographic theory, so curly E represents the energy of the original CFT at some fixed angular momentum and radius of the cylinder. You could just take this angular momentum to be 0. So there's some vacuum state, and then there's some spectrum of sparse states. And at a certain point, you start getting black holes. And while the spectrum is still technically discrete, there's a lot of these states, e to the s of them. And so you get a very dense spectrum once you have black holes that I've drawn as this continuous line, even though it really has very densely packed quantized energy levels. I see a hand conversation going on there. Can everybody still hear me?
Yeah, we can hear you.
Okay. All right. So when you deform the spectrum,
Sorry, maybe I can ask.
Yeah.
Originally, in the first couple of slides, you turned on a source for T because you turned on the gravitational field, which was the source, which I'm thinking of as a source for T.
that's right, on the field theory description.
Yes. And now you've moved to talking about TT bar. It's like a quadratic term in T. What is the connection between those two?
This T, which is the operator that's conjugate to the metric, is indeed the same T that appears in this flow equation quadratically. One way to think about this is that if you think about sources and operators as forming a symplectic geometry in the large N limit, so the sources and operators are sort of conjugate variables. And what something like this quadratic term in the stress tensor does is it's like a rotation in that space that changes what you view as a source and what you view as an operator. So specifically, so if you interpret one of these t's as being a derivative with respect to the metric, they both are, but let's just replace one of these t's algebraically with a derivative with respect to the metric, then what you find is that this deformation is equivalent to if you said your physical effective metric, varied by an amount that was proportional to your stress tensor. Or in other words, that your new metric source is a linear combination of your old metric and the stress tensor operator.
So it's like turning on a source which is itself proportional to the expectation value, or has a term that's proportional to the expectation value. Is that right?
Yes, yes.
Okay. Yeah. Thank you.
Yeah, so so if you thought, right, so it's sort of a less, we don't usually, when we do field theory and we redefine sources, we don't redefine them in terms of operators. We only redefine sources in terms of sources. And operators can be redefined in terms of both operators and sources. So this is in some sense breaking that rule, and that's why we see more general behavior. Okay, so when you do that, what you find is that the t-squared spectrum on the complex plane involves a square root in it. Don't think I actually wrote the formula for it anywhere in these slides. If you are interested in seeing it, I could show it to you somewhere else. But there's a square root expression for the energy of the deformed theory in terms of the energy of the original theory. That's like uh, 1 minus square root of 1 minus this energy. And so what happens is you still have a ground state in the sense of a state that has a smallest real part of the energy. And you still have the sparse spectrum of black holes. But at a certain point, the thing in the square root becomes negative instead of positive. And that means you have to go at a right angle in the complex plane, and you end up with imaginary energy eigenvalues. Now, there's nothing that tells you whether it should be plus I or minus I. So I think the right thing to do is to just include both sides of the square root. So you have both plus I and minus I in the spectrum, which means on the real axis, you also needed pairs of states so that you could have things like two energy eigenvalues come in and then they pop off on the imaginary axis, which actually is a very natural thing to have happen if you write down various non-Hermitian models of physics. This thing where two energy eigenvalues approach each other on the real axis and go into the complex energies happens all the time. What's somewhat special about this theory is that all the imaginary values seem to exist at the same value of the real part. And if you shift the definition of the energy, you could arrange it so that this branch point happens at energy equals 0. And that would tell you that the energies in this theory are the energy eigenvalues are either real or imaginary, but not general complex values. And there's a rapid growth of states as you go out to infinity. This is in the case where there's no bulk matter. In a paper that actually isn't out yet, Roderick and I are going to show that something worse happens when there is matter, which is that the density of states on the imaginary axis is actually going to become infinity. So because the t-squared deformed theory has a well-defined spectrum, it's possible to calculate the density of states on the cylinder. So I did this with Roderick.
Aron, this
And
structure
yeah.
of system, this is one can compute this in general dimension or just 2 dimension. And if general dimension, then you have to work with a particular theory, I would imagine. Because
Yeah, so you gotta say what the theory is. But if you're doing it in pure gravity, it's so we have a general formula in 2+1 and for JT. In higher dimensions, it's a calculable thing in general, but it could get complicated. But There's certainly no obstacle to calculating this density, for example, under the assumption of spherical symmetry, in which case you get qualitatively similar answers to the 2+1 case.
Okay. Thanks.
Yeah. So when you apply the dictionary of this duality, what you find is that so on the boundary theory, you can define what a microcanonical entropy S. So we're literally counting the states in a given small energy window. But in the bulk, you that core so that to calculate microcanonical entropy, what we want to do is we want to take a Cauchy slice, and we take some section of it that's codimension 1 from the perspective of the Cauchy slice, and therefore codimension 2 from the perspective of the boundary theory. So call that lowercase sigma here. And what you find when you calculate this on this tube-shaped region that can have variable area, what you find is that this is somewhat amazing from a boundary theory perspective, but natural from a bulk perspective, that the value of this microcanonical entropy S actually depends only on codimension 2 data. That should read data, not date. So in particular, although the formula does depend on extrinsic curvature of this sigma, it does so in a way that is boost invariant. So if I had a different Cauchy slice that passed through the same surface sigma, I would assign it the same entropy. So from a holographic point of view, this S of sigma bounds the total amount of information that can flow through sigma holographically from one side of the space-time to the other. So the
Aaron, one quick question.
yeah
How are you defining the entropy for sigma, please? I just missed it. I think you said it, but
yeah. So from the boundary perspective,
yes.
it's just counting the number of states.
And that's not infinite?
There's actually a situation where it's infinite, but generally speaking, it's not. It's not always infinite. The
Bar deformation?
sorry, say again.
I mean, in a general QFT, the Hilbert space on any Cauchy slice is infinite dimensional, but are you saying that because of the TT bar deformation, it becomes finite?
No, no. This is so according to this dictionary, where sigma is allowed to depend on the extrinsic curvature of sigma, and one of the components of extrinsic curvature has the interpretation of this energy.
Okay.
So it's actually analogous to calculating the entropy at fixed energy in the CFT.
Okay, thank you.
And that is finite even in the undeformed CFT.
So, sorry, Aaron, if you could go back to the diagram on the next slide. Sorry, I just don't understand this diagram. What are the axes? Is this going into the radial direction?
All right, this is a Cauchy slice at one moment of time. Imagine you have a BTZ black hole, and I take the Cauchy slice of a BTZ black hole.
Okay.
Then that's going to have a geometry somewhat like this because it's a wormhole. So the area expands out as I go to either the left CFT or the right CFT. So so time is not shown because this is a Cauchy slice. And the left to right direction is like a radial direction, and the bulk, and the circle direction is like the angular direction.
Right.
Now, if this were a Euclidean field theory, I would instead think of the circular direction as being like the radial direction of a cylinder, and then this direction horizontally is like a tau imaginary time direction.
Great.
And this is just then a cylinder of variable radius.
Okay, thank you. And in the first part of your talk, you had definite states on the boundary, right? I mean, which were giving you sort of boundary conditions which would propagate.
That's right.
Now you're counting states, so that's confusing me. I thought you're starting with a definite state, and it would be like a
So you don't have to start with a definite state. You could just ask, well, okay. So if you do start with a definite state, so we fixed the geometry of this Cauchy slice, but there's still the operators of this theory, and that includes the extrinsic curvature in the direction that is pointing in the time direction. And that extrinsic curvature is, roughly speaking, the energy of this theory. So if I start with some state on one side and I flow it through, that will determine my energy at every value of the slice. Now I ask you to forget which state I started with. Remember only the energy. And in fact, suppose you only know the energy locally at this particular value of sigma. Then I could ask the question, what's the biggest the entropy could possibly be?
Uh-oh.
And that's what I'm calculating.
Okay, sorry, and the last point I missed. Sorry, I thought you were fixing energy and you're counting how many states.
So take sigma here.
Huh?
Sigma, right? So sigma has an area, it has a geometry, but there's also this extrinsic curvature in the space direction, and there's the extrinsic curvature in the time direction, which is like an energy. So from a field theory point of view, what I'm doing is I'm taking this cut sigma, I'm asking about all the states that have a certain number of energy, and then I'm asking how many states have that property? What's the biggest the entropy could be?
Okay, yeah, thank you.
So it's calculated just by taking the spectrum and counting states. And in the case of the cylinder of variable radius, you can calculate it by several methods. One method I like is to suddenly shock it to a stationary cylinder and just map states between the stationary and non-stationary case. All right. So that's what it is from a boundary perspective, is it's a count of states in a given energy. What is from a bulk perspective is a limit to the amount of entanglement that can be supported by a codimension 2 surface. So from a bulk perspective, this would be like this energy is like the square root of the codimension 2 extrinsic curvature squared. And since extrinsic curvature could be either space-like or time-like, this is something that that ends up being able to be real or imaginary. And so on this theory, what you do not find is that the entropy is always given by A/4. So this makes sense, for example, if I had a very large radius sphere in the vacuum state, or if there's a black hole of very small mass, I cannot, in fact, stuff a very large black hole into that scenario without changing my ADM energy out at infinity. So it's not always true that the maximum entropy compatible with a given codimension 2 data is given by the area. If you can measure extrinsic curvature, you can pin things down more precisely. So in the case where you're on the real axis, what you find is that the entropy is always smaller than the A/4 of the area of the codimension 2 surface. If you are right at the branch point, so that your K, so that your extrinsic curvature is null, so you have a marginally trapped surface, what you find is that there is exactly A/4G microstates in that context. Here, I'm assuming you're in the rotating case, it's actually important that you're on a outer horizon instead of an inner horizon for this to be true. But uh, roughly speaking, yeah. So
Sorry, Aaron.
yeah,
So, I mean, if you go a little bit further along the real axis, then you have some discrete energies. How
well,
does
it's always discrete, but sometimes it's very tightly packed.
I see? So, I mean, if you kind of start exploring further regions, then the fact that it becomes very sparse, what does that mean from the bulk?
These are just states that don't involve black holes. So it's like bulk field theory states.
I see. So you just want to first, okay, look at the black hole states and match it with this. Okay, the area of this surfaces.
Well, you can calculate this thing. You can calculate this entropy even where this spectrum is sparse, but you get a much smaller value of the entropy.
Okay. And for these, when you say k equal to space-like and k equal to time-like, are these the surfaces that are space-like or time-like?
The sigmas.
Okay.
So imagine you have a BTZ black hole.
Yeah.
If the black hole is stationary, then the entropy actually always equals the in the pure gravity case, the entropy always equals the A over 4G of the outer horizon. But if your sigma isn't sitting on the outer horizon, then it may not be the area of the surface that you're sitting on. So roughly speaking, well, no, exactly speaking, in the book, what this thing is basically calculating is if you specify codimension 2 data, and then you ask what's the biggest black hole that's compatible with that codimension 2 data, and then you calculate the area of that black hole on its horizon, that or more generally its HRT surface, that is the core seems to be the bulk dual of this microcanonical entropy.
Okay. Thanks.
Okay. So the other case is the case of a trapped surface, which actually means that sigma is it's behind the horizon. And whether it's behind the black hole horizon or the white hole horizon would be determined by which side of imaginary energy you have. So here's a case where it's nice to have both sides. And in that case, there's more microstates than A over 4G. And I believe this is one of the reasons why tensor networks found it impossible to describe dynamical settings, is because if your Cauchy slice goes inside a horizon, the area can get arbitrarily small as you approach the singularity, the area of whatever is the minimum part of the Cauchy slice. Uh, but it's still supporting the full entanglement of the left and right CFT. So the only way for that to be possible is if the entropy isn't always given by the area. And in fact, in the case of a trap surface, you have to allow for more states than e to the a over 4. That's the only way it can work. Now, something a bit alarming happens when you try to generalize this story to matter. So this is a forthcoming paper with Radek that will describe this. In the pure 3D gravity case, where there's no local degrees of freedom, these trap surfaces are associated with a finite entropy that simply exponentially increases with a Hagedorn-like behavior as the energy goes to plus I infinity or minus I infinity. But it's actually becomes infinite in the case where for imaginary energy, when you have matter. And the reason for that is simply that if you take a trapped surface inside the horizon and you ask the question, what's the biggest that the bifurcation surface of the black hole could possibly be, subject to my codimension 2 constraints, then what you find is that it can be arbitrarily big. There's no constraint. Basically, when you have a surface outside the horizon, it's helpful to think of this from a 1+1 dilaton gravity type perspective. So just in 1+1 dimensions, if you're outside the horizon and you want to place an upper limit on the area of the horizon, it turns out that there's an upper limit that's given by the dominant energy condition that tells you that your black hole can't be too big. That basically any matter in between sigma and the horizon will have to come out of the energy budget and make the black hole smaller. But if you tried to do the same thing in a time-like direction, from the trapped surface of a black hole to its bifurcation surface, you discover that to limit the area of the black hole, you'd want the dominant energy condition with the trace reversed. And there's a reason why nobody talks about the trace reverse dominant energy condition, is that it simply isn't true. So the dominant energy condition would be violated anytime you had a tachyon field. The trace reverse dominant energy condition is violated anytime you have a massive field. This is from a 1+1 dimensional perspective. If you have a higher dimensional perspective, you always have arbitrarily massive fields due to the KK, the Kluser-Klein decomposition down to 1+1 dimensions. So what you find is that it's not possible to place a limit on the entropy when the energy is imaginary and you have bulk matter. And this is not because you necessarily have infinite entropy in an actual physical context. If I make an actual black hole, its entropy is whatever it is. It's just if I ask the question of what's the biggest the black hole could be, given my trapped surface data only, I find that that's not sufficient information to place an upper bound. So there's some other class of black holes other than the one I collapsed that are indistinguishable from it on the trapped surface, but are arbitrarily large. So from the perspective of this deformation, I can follow some finite entropy set of states as the deformation pushes them onto the imaginary axis, and those states will be fine, but some other infinitely large collection of states is coming in from some other class of black holes and sharing the same imaginary energy with it. So that's very annoying from the perspective of constructing a tensor network description because I want to be an upper bound, but it appears to be physically correct.
Sorry,
Hi.
Aron,
Yes.
a question about something probably very elementary to your construction.
Yeah.
Suppose I was in global ADS, not a black hole situation.
Okay.
I specify my slice to be have the geometry of global ADS.
Right. So that could be we're right here, the vacuum state.
Okay, good. Now, is there a constraint on what state I could do that in? So, is there a constraint between the data you specify on your bulk slice and the state that you put at the boundary? Is there some?
That's an excellent question. I'm gonna need to think about it, but it's not obvious that there is because you have you still have the undetermined extrinsic curvature and energy. So it doesn't have to look like the geometry of ADS. It could have a if I put some other state, it could have it could be the same spatial geometry embedded in some different space. Are you worried about the topology of this?
My question was more elementary. I was just what I was trying to understand was if I was trying to do some sort of entropy calculation just in global ADS where I shouldn't expect an entropy, if I try to count all the states that were consistent with some You gave us a map before which
Yeah.
told that if you had a state, we could get a wave function. And presumably there, the fact that there's no entropy would be the statement that if I give you that if I get a particular wave function, that corresponds to a unique state. Is that right?
A particular wave function of Wheeler-DeWitt or of the boundary?
Wheeler-DeWitt wave function. A particular action as a function of these sources on the left-hand side would come from a given, if I specify in the low energy sector, if I specify the left-hand side completely for all reasonable sources, I specify the state. Presumably that's
right. So if you specify the boundary state, then you'll get a single Wheeler-DeWitt state that will have various amplitudes for various Cauchy slices.
good. And so then a particular, at least semi-classical specification of the state would correspond, which have zero entropy. Now I'm trying to contrast that with the black hole situation where you got a large entropy, there presumably you're saying that given the Wheeler-DeWitt data for your slice, there are many different states that
Right. So I think part the important thing in the black hole case is that there's a wormhole, so there's two boundaries. So I can flow my state to the other side.
Yes, but I can specify the data on both sides, right? So I specify one state here, one state there.
Okay, yes.
And now I want to know, is this Wheeler-DeWitt wave function unique? Given a specification of two states, does that give me a unique Wheeler-DeWitt wave function?
It does. Yeah, it does.
It does. So then now I'm trying to understand why there is an entropy associated with this configuration. Why is it different from the global state? I suppose because of two sides rather than one, but could you make that clearer?
Well, yeah, so there's various ways to think about this. You can think of a map from the boundary to the bulk or from the bulk to the boundary. So from the bulk to the boundary, I would fix my Cauchy slice data, and then I generate some entangled state of the two boundaries. And so if you like, what I'm doing is I'm calculating the entanglement entropy between the two sides. If I do that, subject to a constraint on which I could implement with a projection operator on the energy somewhere in the middle. That would be one way to think about it.
I take two different states. I take one state and another.
If you say what your state is, of course, you don't get an entropy. You get an entropy when you allow there to be multiple boundary states.
But if I can tell the difference between these boundary states in the bulk in an easy way, if I have two different states, two different pairs of states, pair one and pair two, and they give me these different Wheeler-DeWitt kind of states in the bulk, then it's like you're seeing the different states in the bulk. That's not like a black hole entropy, right?
That's right. So there's a lot. The statement is that when the entropy is large, in the black hole case, there's some class of states that look pretty indistinguishable if you're just calculating like the energies on these Cauchy slices, or more generally the stress tensor of the t-squared theory.
Wave function, but with only reasonably simple, for only simple operators, it's a many-to-one map. Many states give us the same Wheeler-DeWitt wave function.
That's right. Assuming we don't measure things too precisely, so we aren't measuring like the difference between two nearby energies that are very close energies.
Sorry, Aron, just one quick question.
Yeah.
Do I understand correctly that the entropy that you're talking about here is the entropy associated with this field theory or theory living on the Cauchy slice and of the Hilbert space for a particular sigma?
That's correct.
Okay, and so just one confusion there is usually in a field theory, I mean, I find it, I mean, what is it? The fact that you're specifying the surface fixes the energy and then you get a finite number of states?
It does not fix the energy. You also have to tell me what the energy is.
Okay. Oh, so I see. So the entropy is associated with the surface and a specification of energy?
That's right.
I see.
From
Okay.
a bulk, so what's natural to imagine from a bulk perspective is that I specify like not just the energy, but like T00 everywhere
Okay.
on this slice. So I give you like the stress tensor locally. That corresponds to something like in the bulk that I tell you the geometry of sigma, and I also tell you the extrinsic curvature of sigma everywhere. Now,
Okay.
in the rotationally symmetric context, the only interesting parts, the only things that can vary are this energy and the and the like the pressure, which is the other extrinsic curvature. The and so you've got your uh you've got your your two directions of extrinsic curvature, and you've got your area, and it turns out the entropy is just a function of these things.
I see.
Specifying specifying more derivatives is not useful.
Okay, got it. Thank you.
Basically, you're interested in the things, if you're from a bulk perspective, if you're asking the question, what's the biggest black hole you could have, you only want to talk about things on the surface sigma that can't abruptly change. So it has to be either things where there's a constraint equation that says you can't abruptly change it, or where abruptly changing it would lead to an infinite amount of energy in the bulk.
I see. Thank you.
So, yeah. All right. So, so let's talk about the implications for the information paradox. Now, in holography, the information paradox comes as a tension between the CFT perspective, where we know that the boundary CFT is unitary if evolved in a time direction,
Sorry,
and the yes.
sorry. Just to come back, there are two notions of entropy that one was this entropy along the cylinder that you've been talking about. But
Yeah.
another notion would be the set of all states that give you more or less the same Wheeler-DeWitt wave function. Are those the same notion? Are they supposed to be the same notion? Or
I think they should be the same notion, roughly speaking. We have some argument in our paper to this effect. Yeah, I think you've got to hand wave a little bit, but I think you could argue that semi-classically they're the same notion.
okay, and it's the second notion that I would normally associate with black hole entropy, and then you need the arguments you're talking about to relate it to the first, which is what you've calculated. Is this right?
That's right.
Okay, thank you.
All right, so the information paradox is a tension between the CFT perspective, where we know the CFT is unitary under time-like evolution, and a bulk semi-classical perspective, where it looks at first like it should be. So suppose we have some infalling matter that we could create by some operator inserted into the CFT. So it forms a black hole, and we could take what's called a nice slice, shown as this green surface. So this is a slice that stays away from the singularity, where it's obvious that semi-classical physics breaks down, and it covers the full history of whatever fell into the black hole. So it includes the infalling matter, and it includes the Hawking quanta that come out, and it includes the partner pair modes of the Hawking quanta that fall into the singularity. And then the question is, if you think that the information somehow comes out of the Hawking radiation restoring unitarity, how do you reconcile the fact that this infalling matter, the Hawking quanta, and the partner modes all live on the same slice? So how do you avoid the no-cloning theorem? So this is one way of saying what the information paradox is. So what I'm going to do on the next slide is I'm going to draw a picture of this green nice slice and these three types of matter. But I'm going to draw it as a slice. So here it is. So you've got something like a tube, and it's closed off because this nice slice goes to the origin here. And the first thing that comes is that you have the black hole forming from collapse. And that comes from this infalling matter here. And that I'm showing here. Then you have the gradual evaporation of the black hole. And at various points along that process, you have the partner radiation that is here. And then at some point, you cross out of the horizon and you come to this ADS region where the Cauchy slice goes off to infinite area. And there you have the Hawking quanta living there. And as you asymptote out, this thing connects on to the usual ADS-CFT description. Now, suppose we view this from the TT bar type description, from the Cauchy slice holography description, that we think of there as being a field theory that lives on this tube-like thing. So it starts here by creating some state. And since this is closed off, we get some particular state. But then we encounter these three types of matter. And the three types of matter can affect the sources that exist on this field theory. So the ultimate state we get on the CFT depends on these sources that shows up in this partition function. So then when we evolve from left to right, we get the CFT state. Now, as long as these sources, if these sources were all pure, and by pure, I just mean some coherent superposition of a choice of different sources, not some probability distribution over some set of sources. So as long as the sources are all themselves pure, then from the perspective of the t-squared theory, it's actually manifest that the state we get out at infinity will also be a pure state. And that's just for the usual reason that if I have a partition function that has only one boundary, then I get some pure state of that boundary Hilbert space just by linear algebra or whatever. The only way I get an entangled state, a mixed state, is if I have multiple boundaries and I restrict to looking at just one, or I have a probability distribution over my sources. So you could, of course, get a mixed state if it turns out the infalling matter is mixed. But since we're trying to make the information puzzle as sharp as possible, we're going to say that that infalling matter is in fact pure, and so that we potentially could reconstruct it. Okay. Now, if we match onto the semi-classical description, even if the infalling matter is pure, of course, there's entropy introduced by the Hawking radiation. And so in that case, it's not true that the Hawking sources and the partner sources are pure when taken in isolation, but they purify each other because they're created in some entangled state. So the way you should think about this, you could think about it somewhat in a pictorial way by imagining that the state of the Hawking quanta, the entangled state of the Hawking quanta and the partner quanta are represented by some tensor network, which has tensor network edges that connect the entangled pairs. So from that perspective, when you specify the source the source that lives on this theory, you have to remember that some of the sources that are long distances away are entangled with each other. But this does not change that the boundary state we generate by this left to right process should be pure, because the sources taken as a whole are still pure. Okay. So now, essentially, the same story will obtain if we pick some arbitrary surface sigma at some point during this evaporation process. But now, instead of Hawking modes and partners, we should consider the field theory entanglement across this sigma. Now, something nice happens if this nice slice contains a marginally trapped surface. If it contains a marginally trapped, if this sigma happens to be a marginally trapped surface, and maybe with my description of the process, it would have made more sense if that was out here on the right. Well, anyway, let's just say this is a marginally trapped surface. Then the classical entropy is given by A over 4G. So this holographic entropy bound will be A over 4G. But because of the extra tensor network lines, the maximum information flow across sigma is presumably then given by the generalized entropy. So we take into account quantum, these quantum extra legs, the bound on entropy will not be given just by the area of this sigma. It will be given by a generalized entropy that includes a contribution from the entropy of all of these lines. This formula gives us a sort of information bottleneck formula, which is a maximum of information flow allowed that is given the specified area and extrinsic curvature data and the information about this amount of entanglement. So now suppose that we consider we cut this thing at this place. And what we want to do is we want to consider just the part of this diagram that is to the left of sigma. So there's a question, do we ever get into trouble in this reconstruction process? Is there enough information on sigma to encode what's behind sigma? But this actually depends on your interpretation. So if all you're trying to do is to reconstruct the infalling matter, then you're actually always okay in this sort of situation, because the generalized second law tells you that A over 4G plus entanglement is always increasing through a black hole process. So I always have a greater amount of generalized entropy on sigma than I did when the black hole before the black hole formed, when my entropy is just whatever information is in the infalling matter. So it follows that if all I want to do is reconstruct the infalling matter, I always have enough information on sigma. So it seems at first like there's no problem. However, this depends on the choice of interpretation. In the interpretation I just said, we're thinking of the Hawking partner edges as a resource that we're just using as a tool to determine the infalling matter. In fact, we could be more aggressive or ambitious. We could say, what if I say I want to reconstruct the infalling matter and I also want to reconstruct the Hawking partner pairs? In that case, I'm no longer allowed to use these edges as part of my tensor network. because I suppose, for example, I wanted to not only reconstruct the infalling matter, but explicitly verify that the partners were entangled with the Hawking modes in the expected semi-classical way. In that case, I have to reinterpret these partner modes as logical qubits that I'm trying to recover. And now I have to recover the infalling matter and these logical qubits just from the sigma bound without any extra edges. And so on this interpretation, the partner mode, the Hawking entanglement makes things worse, not better, because I'm trying to reconstruct more things and I don't have an increase of area. It moves the entanglement to the other side of the inequality. So if we think of the partner modes as logical qubits, the tensor network lines go away and a different inequality becomes relevant. I need the amount of entanglement to be less than A over 4G. And if I want to reconstruct the infalling matter in addition, things would get even worse. Even without worrying about the infalling matter, this inequality is going to be violated after the page time. If I instead made this infalling matter an arbitrary state, and I wanted to reconstruct all of it, I would in fact get a problem very quickly. But I already stated that we can't violate purity of the boundary state. So it appears that the only possible thing that could happen in this theory is post-selection, that the partition function z actually maps multiple bulk states to the same boundary state. So the conclusion here is somewhat similar to the Python's lunch idea that people have been exploring with various tensor network models of the black hole interior, but now with an explicit holographic continuum model of the bulk. So the entropy bounds restrict the total amount of information that's behind the bottleneck surface, but it does so in a way that's difficult to detect with simple measurements. Unlike the Python's lunch story, there's no obvious connection to gate complexity per se, but the post-selection, in order to not run into post-selection, you just have to try to not measure too many partner modes. So there's still a notion of simplicity where more ambitious things are harder to fit through the bottleneck than less ambitious things. In some way, the proposal here is similar to the spirit of the Horowitz-Maldacena final state proposal. The difference here is that Horowitz and Maldacena propose that post-selection occurs in the bulk dimension at the singularity. And here, the claim is that post-selection occurs at some point in the Cauchy slice on any given nice slice. So rather than something you have to understand the singularity for, it's something that occurs on every slice, whether it's close to the singularity or far from the singularity. So it doesn't have anything particular to do with the singularity. It's also worth pointing out that the analysis becomes in some ways more interesting if you consider a trapping horizon that is actually foliated entirely by marginally trapped surfaces, because then you would get that your number of states goes like A over 4G at every point in this process, and the you would have a natural interpretation of the second law along such a direction, which Netta Engelhardt and I showed how to think of that second law on the trapping horizon as having a statistical interpretation in terms of this maximize the entropy of the black hole. All right, so that's what I wanted to tell you guys. Now, feel free to have even more questions.
We'll clap first. Okay, questions? Okay, maybe I wanted to make sure I understood the last part. So
Yeah.
what I got from it, and please, maybe I misunderstood, but maybe what I got from it was that if we are at, let's say, the horizon or some surface, and we can use your previous ideas to compute the total number of states associated with that, with the cylinder cut at that surface.
That's right.
And
So far.
then, if the number of states, number of ways of doing it of the inside was larger than that, then that would tell you that many of those different things led to the same state.
Correct.
Okay, yeah, thank you.
Right. So the only subtlety there is that, yeah, you could in the case where you don't want to reconstruct the Hawking, you don't care about reconstructing the Hawking radiation and its partners. In that case only, they can help you reconstruct more information than you would otherwise be able to reconstruct just through the area alone.
Zoom questions. Okay, one more general question, please, Aron. You had you said that this way of thinking, the way you're defining this the state through the partition function, as you said, it's sort of clearly meaningful at large n, basically because you could compute an effective action and then turn on sources, and then it's just a classical problem. But you also indicated that might be well defined at order by order and the 1/n expansion. I wanted to hear a little bit more about.
Okay, so yeah, that's a lot more subtle. So we have an argument to this in the paper with Gonzalo and Rifat, but it's a bit tricky. So I'm not 100% confident we didn't make some bloopers. But the roughly speaking, you need to consider something like bulk loop corrections. And to do so, there's potential problems you get with this deformation from the fact that you're defining two operators, the stress tensor, at the same point. So you need to introduce some sort of regulator, like a point split, for example, between the place where you introduce the two stress tensors, and then you need to work order by order in that thing. And it seems to work, at least formally. I think it can probably be made to work if you do it in the correct way, but I can't necessarily rule out there being some technical problems that we didn't properly address. But I suspect they're resolvable. Since this would be holographically dual to just some sort of like finite loop order in the bulk. So where you don't encounter the full quantum gravity problems. The one thing about just the equations that happens when you do this, it turns out that weirdly the mathematics works out the simplest. If you remember that what you're doing is only valid in the 1/n expansion, but you actually don't try to calculate Taylor expansions in 1/n, you try to calculate the full thing, because, well, it gives you it's a way of avoiding some annoying logs or something like that. But anyway, there is a discussion of this. There is a discussion of this in our paper. So it appears at least formally that when you do this thing at finite loop order, you just have sort of like normal field theory divergences to deal with.
Okay, thank you. And one other question, maybe you said this, maybe it's obvious, but when you talked about the wave function as a function of data right at the beginning of your talk, you talked the partition function as a function of data and connected it to the Wheeler-DeWitt wave function. Now, the Wheeler-DeWitt wave function, the Wheeler-DeWitt wave function obeys some constraint equations.
That's right.
which do they come from sort of from conformal invariance of this?
They do. So you start with, so if you start with your CFT, the stress tensor obeys two equations. One is that it's conserved, and this looks just like the spatial diff constraints of GR under this dictionary. The second is that the trace is either 0 in odd dimensions or it obeys the anomaly equation more generally. This doesn't look like the Hamiltonian constraint, but the deformation mutates it into the Hamiltonian constraint. So your seed CFT obeys little d plus 1 constraints on the stress tensor, and so does the ADM formulation. So this deformation that you pick is constructed to deform the thing. And basically, roughly speaking, every new term you have in your bulk Hamiltonian constraint, you need a new term in this deformation, except the ones that are purely marginal that map onto some sort of anomaly in the CFT.
Pretty much. Any other questions? Okay, if not, maybe we can thank Aron again.